Joining us from the State Hygienic Lab at the University of Iowa is Majid. Majid's talk will focus on the analysis of PFAS in the environment. Certainly a very hot topic at the moment. I think what's unique here is the challenges that PFAS presents as a target analyte. Of course, PFAS is not just a single molecule, but a whole class of compounds that are ubiquitous on almost everything we touch and use. And this presents some unique challenges when it comes to chromatography of the method, for sure. And finally, compared to the previous speakers we've had today, you might think water is the simplest matrix to work with, compared to meat products or plasma or tissue. But you'll see today that even something seemingly as simple as water presents challenges as a matrix when trying to build an accurate and precise method. So welcome, Majid. The floor is yours. Please go ahead.
Well, thank you so much, Ian. Hope that you guys see my slides and hear my voice clearly. So thanks so much for the SAICS people for the invite to come in and present about the PFAS program that we're holding down here at the Iowa State Hygienic Lab. So hopefully I will make it an easy 20-ish minutes to go through about the PFAS program and how we are handling the PFAS testing here in the State Hygienic Lab. So again, my name is Majid and I'm environmental scientist here at Iowa State Hygienic Lab. It's a public health lab that we serve the state of Iowa. We do a lot of biological and environmental testing, and that's including PFAS in water and different matrices. So we'll make a quick in here for those who are new to the PFAS. We'll give a quick overview about the PFAS and what we know about these chemicals. And then we'll go through the PFAS method testing that we are doing here at the State Hygienic Lab and how we are handling the PFAS analysis. And then we'll talk about the State Hygienic Lab testing process and the quality control as well. So in the quick and simple term, these PFAS are got invented in 1940. They are simply fluorocarbon structures where they are either partially or completely fluorinated. So the carbon fluoride bonds giving these chemicals and the structure very unique chemical and physical properties to make them really tough, to resist temperature, repel water, oil. So that makes them useful to be used in a lot of applications since got invented in 1940. So these chemicals are around us for many, many years since 1940. And taking into account that we are using a lot of consumer products and commercial products that are some sort having some PFAS in them. So most of the communities, especially here in the United States, they have been exposed to the PFAS to some sort of level. So, and recent study, they showed a lot of health problems, issues like cancer, cholesterol, immune response, pregnancy and childbirth issues that are related to PFAS. Now, for sure that there are a lot of studies right now trying to figure out these relationship between the PFAS exposure and many, many health problems that's still being studied right nowadays. But in between, how we get exposed to PFAS from drinking water to the air that we breathe in and consuming the products that come in contact with PFAS, yet it has been identified that the main source of exposure for the PFAS are the drinking water. So taking into account that PFAS are highly mobile, so when they are out in the environment, they can easily move from the soil, they can go to the groundwater, river, lakes, and then they add them to tap water, drinking water. So exposing to PFAS from drinking water is the main thing that everyone is looking for. So in that term, EPA start to regulates and publish and validate method to look at the PFAS in drinking water. So we're talking mainly about most of the two common methods that are known about PFAS in drinking water, method 537.1 and 533. we are here at the State Hygienic Lab. We're trying to keep up with the EPA methods in terms of emerging contaminants, and PFAS one of the hot topics. So we start to work on validate both of the method 537 and 533 to make them available at the lab so we can start doing PFAS testing and monitoring across the state of Iowa. So we start with the EPA 537.1 and we get the validation done in 2022. And then we start after that to get the work done on 533 and get it authorized and approved in 2022. Now, for sure, in simple term, the main difference between 537 and 533, it's the chemistry and the extraction between basically C18 columns and then wax column. But the most important thing is that you can see the difference at the list of the analyte. 537 has 18 analytes to monitor versus 533, it's basically 25 analytes. And then 533 using the labeled isotope, which is a technique that makes it more accurate and precise. Taking that account that we're living here in the state of Iowa, and we have a lot of small communities that basically having their source of water coming from groundwater and well water private wells. So we find the need that we need to extend the scope of the method. So we extended the scope of the method to not only test for PFAS in clean drinking water, but we also were able to look into validate the method to look at the surface, raw, and well water, following the same EPA rules for these two methods. Now, the testing process here, when it comes at the PFAS in our public health lab, it takes a lot of steps from sample collection to data review and result and report back to the clients. Now, taking that account that we are in public health labs, we do a lot of QC check when we do a lot of measures when it comes to testing, especially with PFAS, to make sure that whatever that we report back to the clients are true value. So our process chain is basically starting with a sample collection when the client come or call our client service, and then they place an order for PFAS to choose in between the two methods. Once the sample being collected, then we receive the sample at the bench, and we do a lot of like pH, chlorine testing, and we do a lot of QC prep at the bench to make the batch ready to go for the next step, which is doing a cleanup and extraction for the PFAS using solid phase extraction. Once we extract the PFAS from the sample, which is in the drinking water is 250 ml, then we treat the final extract from the extraction process and make it ready for the LC analysis. In the LC analysis, we do quantitative analysis when we do a lot of like QC check, and then we create a calibration curve to measure the PFAS level in the sample. Then we do the review for the data, and then we do the QC check to make sure the method and the performance are met and there is no QC flag. And then we report back to the clients using our LIMS system. Now, in simple term, you see these are steps, but under each of these steps, we have a lot of QC control, and we have a lot of measures that we do to make sure that our PFAS testing in here for the quantitative analysis are being met, and the method performance are within the scope, and we don't have any deviation from what we expect for the method. So starting with the sample collection. So with the sample collection, we realized that collecting the sample is the key. Knowing that PFAS are around us and the source of contamination could be happening at the field during collecting the samples. So we took a measure to make sure that when we collect the sample or the client collect the sample using our collection kit, that we minimize the contamination at the field. So one of the things that we did is we put our collection kit in a way to control the contamination happening on the field. So you can see the picture in here. When we send out the collection kit, we send a cooler with a set of bottles, and these bottles basically have been tested to be PFAS free before we send them out to the field. In addition, we also send out organic free water that's being used to collect the field blank at the field. So we ask the client to collect the water at the same time they are collecting the sample, And that water that we send out also being tested to be PFAS free before it go out to the field. One other thing also we have observed is that collection for the PFAS is not easy in one term or another. So we came up with the idea about creating a collection instruction that has also a visual guide to help the client easy collect the sample and also pack the samples, label them, and then send it back to us in a way to minimize the contamination at the field. So since we implemented both of these techniques with our collection guide, we have seen less issue when it comes to cross-contamination at the field, and then less request to recollect the sample or reject the sample. And then once we collect the sample and then we receive it at the lab in here, we accession the sample and we make the sample ready for the batch. So the sample preparation for the method in between 537 and 533 include a lot of like QC prep with each batch. And that's basically according to the EPA method. So we do the lab reagents, which is basically the previously tested water that we know it's PFAS free. We use it to control the contamination coming from the lab space. We also test the field reagent blanks that we send out with the collection kit, which is basically previously been tested to be PFAS free if we see any positive hit in the sample. So that will give us a way to see if there is also contamination if we see any positive hit within the field blanks itself. We also do a lab fortified sample. This is a different level to control the method performance, and we do matrix effect also for the sample. For the method 533, for sure, we're using labeled isotope, which is more of a accurate technique that we spike all these reference materials into the sample, and then we monitor the recovery afterward to study the performance of the extraction and the method. During the sample prep, one of the things and the keys that we are doing and the measures to make sure that we don't have a lot of contamination or failure during the extraction process is that when we're using the lab reagents or the lab fortified, the water that we're using to sample these QC, we're using a water that we are testing in the lab, and we know it's a PFAS free and everything is under control. And we're also using a specific area in our lab to do it for PFAS testing and nothing else. And when we do the pH measure or the chlorine measure for the UCMR5, for example, we don't dip the pH probe or the strips inside the water. Instead, we do a simple technique. We take an aliquot and then we measure the pH outside. One of the things also to make sure that we keep monitoring our method performance is that when we do the lab fortified, we do low, mid, and high to make sure that we're testing our method across the calibration range that we're using. We also, for the analysts, they are prepping the method blanks that goes with each sample, with each batch, and that's to be an extra measure to control the contamination coming from the solvents being used for the sample prep. When we do the mass effect, we don't really choose a clean sample to do and study the matrix effect. And in fact, what we do is we create our list for the day, and then the analyst will pick the first sample in that list, no matter if it's a clean sample or it has some particulate in it as a raw water. This will give us a variety of testing the method from batch to batch across different matrices. And then once we prep the sample, then the next step would be the extraction and the cleanup. And in a simple term is a solid phase extraction cartridges being placed on the unit, and then we condition the cartridges to make them active. We pass the sample through them, and then we catch the PFAS on the sorbents, and then we do an extra washing and then elute the PFAS from the column, collect them in a tube, and we call that one as a final extract. With the method 537, it's basically similar to a C18-based sorbents, and then we're using a wax anion for the 533 to capture the 533 list of analyte. And that's basically according to EPA published method. During the sample extraction process, what we do here in the lab also as a measure to make sure that the method is in control, we do a great job at refreshing all the solvent beforehand or when needed. We also pay specific attention to the buffer and the basic methanol for the method 533 to make sure they are daily prep. We do a lot of QC and track for the lot numbers when it comes to solvents and SB cartridges. So every time we get a new lot of SB cartridges, we test them to make sure they are PFAS free. And same goes with the solvents and the water. So the water and the solvent, for example, the methanol, we do in-house testing to make sure each new lot is PFAS free before we put them in use for the extraction. And we also switched from manual extraction to automated extractor unit. This is to give us more of a way to minimize the cross-contamination, improve the proficiency for the test, and also increase the capacity and less of hand needed when it comes to the extraction. So since we switched to that unit, the unit helped us to increase the capacity and also having a more of a control and better recovery when it comes to the method performance for both methods. Once the sample being extracted and we collect the final extract, then the next step would be sending the sample for the LC analysis. What we do is, you can see down here, we're using an LC mass spec from SciEx. That's the 6500 treble quad, and we're using it for quantitative analysis. Which means basically we're using a calibration curve as a reference, and we calculate the PFAS analyte in each of the samples at a specific limit. Our quant limit for the method using the SciEx 6500, we are targeting, and we have the quant limit being set at 2 nanograms per liter. So that's 2 parts per trillion. We have that level 2 part per trillion for all of the analyte in 533 and 537. If you were to compare that with the final MC level that has been published and will be enforced in the next few years, so the EPA final MCL is sitting at 4 parts per trillion. Our method is basically we can look at 2 parts per trillion, so that's basically 2 units below what's needed for the EPA regulation. So the LC method, simply we're using something similar to the published EPA method, where we're using 15 we're using like mobile phase. It's 20 millimolar ammonium acetate in water, and using methanol as well. Our run time is being set at 15 minutes, so that's way lower than the published method. It's with the system that we're using right now and the method that we develop and modify. It's basically a very robust method that we only need 15 minutes on the LC run. We're also using a delay column to help us capturing any contamination coming from the LC unit. For the analysis on the LC, we're using a C18 analytical columns for the separation before being sent to the mass spec. So on each test and each batch, things that we do on the LC side also to make sure that we are having the method under control, we flush the LC unit with methanol for 15 to 30 minutes beforehand. This is just to ensure that we are cleaning if there is any PFAS residual within the LC unit or the line. So we do a 15-20 minutes purge, we send it to the waste, and that helps us to clean up the system beforehand. The delay column that we are placing into the LC system, which is basically in between the mixer of the LC and the injection valve, help us to capture and delay any PFAS analyte coming from the solvent. And for sure, as I said, with the extraction, we use only tested solvent when it comes to the LC, and that's the water and methanol, just to make sure that we're testing it in-house before we put it in use. We also, when it comes to the LC system, we are using peak tubings. That's basically to bypassing the degasser and make sure that there is no contamination coming from the LC unit itself. This is per the EPA recommendation and the LC manufacturer as well. Within the LC method also, we implement a syringe and injection valve washing from injection to injection, just to make sure to give the system enough time to flush and rinse before we do the next sample. And we're also using LC guard columns. The LC guard columns helping us to capture any particulate, and also we make sure that there is no PFAS coming from the guard columns itself. And then the next step will be the mass spec. As you said, we're using a SIGES triple quad 6500 for the mass spec analysis. That's basically equipped with the electrospray ion source. With the Tandem Max, we're using MRM monitoring with negative modes, and we also optimize our temp to be 300 and gas 1 and gas 2 sitting at 50 and 60. So the Tandem Max, basically, it's when we do that one, we monitor the fragmentation for the parents and for the parents and the daughter ions that are going through the collision cell. Things that we do with the mass spec is that once we, our way is that during the method developments and validation, we're basically do unscheduled MRM to study the method and the method performance beforehand. And once we have enough data to switch to the MRM, we switch to the MRM mode, where we fix the retention time and the fragments that help us to better quantitate the analyzed on different levels, and also helping us to remove any of the delayed peaks that are coming from the solvents. We also optimize the target cycle time, which is basically a feature in SciEx, to give us enough points across the peak, which is optimally between 10 and 20 points. When it comes to developing the LC run that's being linked to the mass spec, we also make sure that we give enough time at the end of the run to flush the unit with methanol, and enough time at the beginning also to equilibrate both the LC and the LC columns and the mass spec. And then once we collect the data from using the acquisition method on the SciEx-OS, we also do the quant method. So the quant method is basically using the SciEx-OS software. That the software is great on building a great quant method. We have used that SciEx-OS for peak integration. We can set the retention time, peak parameters, and the calibration curve within that window for each of the specific analyzed, and being safe in the quant method. Within the SciEx quant method also, you can create a calculated columns. So what we use, basically, we use the calculated columns in our method to calculate for the recovery for the IPSs, stable isotope, and the surrogate, and we also calculate for the final concentration. So we have a calculated columns where we calculate the sample volumes based on the weight, and then we calculate the final concentration in between the calculated concentration and using the final volume of the sample itself. We also use the calculated columns to look at the QC recovery for the lab fortified MS-MSD, and we're using it also to create a custom columns to calculate for the pure recovery on the MS-MSD using the N45 sample level. Once we create the calculated columns within the quant method, we also have flagging rules. The flagging rules is something that we use to apply specific range and criteria into each of the calculated columns, so that when we are processing the data, if everything is outside the spec, it will flag it within the result table. Down here, it's you can see that's a busy looking result table from SciEx-OS. This is only for one sample. If you can see that we have different calculated columns implemented within the quant method, and we have different flagging rules, and you can see under the calculated concentration, the flagging rules comes up when the calculated value is above what we define it in the flagging rules. And then under the reported recovery columns, you see also a couple of flagging rules when some of the QC criteria is outside the range. So in between the calculated columns feature and the flagging rules, the quant and the analysis for the PFAS analysis is going smooth, where we can monitor anything outside the spec. Throughout the last few years, we also participate in different proficiency testing for both method 537 and 533. We do the water supply PT testing. We also did the UCMR5 proficiency testing, and we successfully passed all the PTs for both method 537 and 533 successfully. The next plan for the PFAS program at the State Hygienic Lab is to keep working on bringing more methods in line, especially 1633, to look for the non-drinking water, biosolids, sediments, and tissue. Recently, we developed a method to look at the PFAS in serum and plasma, and we just finished the validation for that, and we're hoping to get that one in protection very soon. And for sure, we're looking to increase the capacity and increase more instruments, bring more instruments to the lab, and as the demand increase for the PFAS testing. One thing also I want to point down here is for all the audience is that we are planning for a conference here in Iowa, which is going to take place next year, April 15 and 16. So that conference will focus mainly on PFAS. We have 2 days for that event. Day one will be all about environmental testing, PFAS and environmental testing. And day two will focus on PFAS and biological testing. So we're really looking into people to come in, participate, and share their connect with each other and share their thoughts about PFAS and learning about PFAS in that conference. So please keep an eye out on that conference. And if you have any question, reach out to me or Chris. Now, finally, I would like first to thank our PFAS team at the State Hygienic Lab, John, Matt, and Jessica, for their great work on keep doing the PFAS testing and building more and more robust program here to test for PFAS in different matrices. And many thanks to the SAICS people for the invite down here. And with that, I would like to end my talk and open the floor for any question that you guys may have.